When an object hits another object, let's say object 1 hits object 2, object 1 will experience a certain impulse, either positive or negative. Object 2 will always, every single time, experience an equal and opposite impulse. So if the impulse on object 1 is 10, then the impulse on object 2 is negative 10, right? If the total, or if object 1 always experiences equal and opposite impulse to object 2, then that means that the total momentum is staying the same. That's what the law of conservation of momentum tells us. It tells us that if we have an isolated system, and I'll tell you what an isolated system means in a moment here. If we have an isolated system, then the total momentum will always remain constant. Each individual object's momentum will change. Object 1 will gain momentum, object 2 will lose momentum, or vice versa. But the total momentum will remain the same if we have an isolated system. Does anybody know what an isolated system means? Yeah, nothing can come in or out. We define that in physics usually a little bit more simply as saying we don't have any external forces. No external forces. Like, give me an example of an external force. Friction. Friction, air resistance, things like that. Now the reality is sometimes we have friction, right? Sometimes we have air resistance. So what we usually want to do when we're analyzing a problem using conservation of momentum, because it requires us to have an isolated system, what we usually want to do is examine the momentum immediately before and immediately after. Why? Well, because if there's friction and we're looking at the problem just after, like a fraction of a second after the collision has taken place, well then friction hasn't really had a chance to do anything. Right? Does that make sense? If we're looking at just before, it doesn't matter what was happening 3 seconds before the collision. If we look at just before the collision took place, then there were effectively no external forces. And if there was external forces, or if there were external forces, then they didn't have a chance to do anything. So it's as if they weren't there. If we look at the momentum just before and just after, it will be the same every time. Now, of course, we mentioned this, we alluded to this before, right? The total momentum remains the same, but that doesn't mean that the momentum of each individual object remains the same. It can't. When two things collide, and if the velocity changes, which they do clearly when two things collide, we're going to get a change in velocity, therefore we're going to get a change in momentum of each individual object. We're just saying that now if we analyze the total momentum of the system, then the momentum will remain the same. We can use what we're about to learn as a problem-solving method, the law of conservation of momentum, to solve a problem if we're looking at the system. But we can still use impulse to solve a problem if we're looking at an individual object within the system. If you guys were all running around this room right now, colliding with each other, we could look at those collisions as a whole, like using the mass and velocity of everybody in the room, if we use conservation of momentum. But if we wanted to use impulse, we'd have to pick Jackson and analyze Jackson in the collision and not everybody else. The last topic we did, impulse, we derived from Newton's second law. We're going to derive this one from Newton's third law. You guys remember what Newton's third law says? Object A applies a force on object B applies an equal and opposite force on object A. We used that, right? We've used that already when we talked about impulse. But we used the second law, F is equal to m times A, to derive the equation for impulse. We're going to use the third law to derive the equation for conservation of momentum. Newton's third law says, well, mathematically, it says we'll say F12, the force of object 1 on object 2, is equal to negative F21, the force of object 2 on object 1. Negative because it's equal but opposite. Now F12, the force on object 2, is going to be m2 times a2 equals negative, well, this is the force on object 1, negative m1 times a1. Agree? So I guess we're using Newton's second law here as well, but it stems from, it starts at Newton's third law. Let's sub in delta V over delta T here. Let's say m2 times delta V2 over delta T is equal to negative m1 times delta V1 over delta T. Why did I not put the subscript for delta T? Why did I not worry about delta T1 or delta T2? I just called it delta T. Yeah? Yeah, times a scalar, yeah. Okay, that's not what I thought you said first. It's the same, right? Time is a scalar, absolutely, but it's the same for both of them, right? The collision lasts 1 second, it lasts 1 second for both of them. So that means I can cross that off, I can cancel it out, because it's the same time for both. So now I got m times delta V2 equals negative m1 times delta V1. Let's change the delta V into m2 times V2F. That makes sense what I mean there? V2, object 2, final, minus V2I equals negative m1 times V1F minus V1I. Now let's distribute the masses. Do you know what I mean by that? Distribute the masses? Multiply the masses by everything inside the brackets. I get m2 times v2f minus m2 times v2i equals negative m2 times m1 times v1f plus, because negative times a negative is a positive, m1 v1i. Now let's just change the order of that around a little bit. If we do, we end up getting this. m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. Realistically, you're not going to have to derive this equation. Like you realistically are not. Okay? But you do need to know that it comes from Newton's third law. And the reason that I derived it was to prove to you that it comes from Newton's third law. What do we have here? m1 v1i, well, that's the initial momentum of object number 1. m2 v2i, the initial momentum of object number 2. So what we're saying is that this is the total initial momentum. And this, m1 v1f, that's the final momentum of object 1. m2 v2f, the final momentum of object 2. That's the total final momentum. So now we're saying that the initial momentum is equal to the final momentum, which is exactly what we just said, right, a few minutes ago. In an isolated system, the total momentum remains constant. We don't gain or lose momentum if we have no external forces. We want to do 2 examples today, starting with example number 1. It says a 1,500 kilogram car traveling north at 20 collides with a 1,700 kilogram car traveling south at 21. 2 cars entangle. That means that they stick together, right? The metal intertwines with the metal of the other car, and they go off as if it's one car afterwards. Determine the velocity of the wreckage, this whole wreckage, immediately after the collision. Notice we say immediately because we don't want external force to have a chance to come into play here, right? In other words, we want an isolated system. We could, if we wanted to, analyze this problem using impulse, but if we did, we'd have to pick either the 1,500 kilogram car or the 1,700 kilogram car and not do them both at once. Okay, we're not going to do that. We're going to use conservation of momentum and analyze the system, everything at once. We're going to say M1 is 1,500 kilograms. We're going to say that V1, object number 1, initial V1I, okay, the first car before is moving at 20 meters per second. Oh, what should I have done here? What should I have done that I didn't do? Direction, north and south, right? V1I is 20 meters per second. Let's say M2 is 1,700 kilograms, and let's say v2I, that's the initial velocity of car 2, is negative 21 meters per second. Negative because it's to the south. They head off as one. We want to find the velocity after the collision. We're not going to call it v1f. We're not going to call it v2f. We're just going to call it vf because there is only one velocity afterwards, right? Now, if I was doing impulse, I'd pick object 1 or object 2. If I'm doing conservation of momentum, I'll do them both, the whole system. How many objects do we have before this collision takes place? 2. So let's say m1 v1I plus m2 v2I. Here's the momentum of object 1 and 2. Equals, how many objects do I have afterwards? 1. So I'm just going to call it mvf. I'll call it mt. What do you think T stands for? Total. The total mass times the final velocity. Does that make sense? Okay, let's sub in some numbers here now. 1,500 times v1I is 20 plus 1,700 times negative 21 equals the combined mass is 3,200 kilograms times vf. So what we want to do here now, of course, is to get the left-hand side, 1,500 times 20, and then combine that with 1,700 times negative 21, and then we'll divide it by 3,200, and we'll solve for VF, and we get negative 1.8 meters per second. So the velocity of this combined record should be 1.8 meters per second. You can imagine how maybe you're a traffic accident analyst for a police force. You can imagine how maybe you do something like this when analyzing accidents, but you probably wouldn't be looking for VF. You'd probably be looking for VI. How fast was the car moving before it crashed, right? Was he speeding before the crash took place? All right, let's take a look at example 2 now, and then we'll wrap it up. It says a 0.006 kilogram ball moving at 3 collides with another 0.006 kilogram ball traveling 2 to the south. First ball moves off to the south. What's the velocity of the second ball immediately after the collision? It's an isolated system, immediately before, immediately after. Let's write down some givens here. We're going to say that the first mass is 0.0060 kilograms. Actually, they both are, right? We got a velocity here that's 3 meters per second to the north. So it's positive. But what are we going to call it? Is it V1 or V2? V1 or V2? 1. Yeah, it's V1. Is it V1I or is it V1F? This is I. This is the initial velocity of object number 1. We have another velocity here that is negative 2. Because it's to the south, right? Is that V1 or V2? 1 or 2? This is object 2. Okay, this is object 2. It says another 0.06 kilogram ball traveling to the south. This is the second object. Is that V2I or V2F? This is I. Yeah, this is V2I. Good. Now, we have another velocity here yet. This is negative 1.0 meters per second. Is that negative 1? The first ball moves off at negative 1. Is that V1 or V2? 1 or 2? 1. I or F? This is F. This is the final velocity of the first car. What are we looking for here? The velocity of the second car, that's going to be V2. Afterwards, that's V2F. So let's say if we're analyzing the system, PI equals PF, M1 V1I, object number 1, plus M2 V2I, object number 2, equals, how many objects do we have afterwards? 2. M1 V1F plus M2 V2F. Now, I spot a bit of a shortcut here that exists in this one that didn't exist in the last one. Jake, you see what it is? Yeah, since the masses are all the same, they cancel. Now, I'll tell you what. With conservation of momentum, units also cancel. So you can get away with a conservation of momentum question using units other than kilograms or meters per second. If you were given the speed in kilometers per hour, you could use that here because the units cancel, because the units appear in every term. Does that make sense? If you're not comfortable with that, what should you do? Convert them to meters per second if you're not comfortable with that. V1I, 3.0. V2I is negative 2.0. V1F is negative 1.0 plus V2F. This is a 1.0 on the left side, negative 1.0 plus V2F on the right side. Take that over, V2F equals 2.0 meters per second. There are 7 questions on worksheet number 3. I would like you, please, for homework, in addition to preparing for your quiz on Monday, to do the first 5 questions on that worksheet, worksheet number 3.